Good day, grade 11s. Welcome to our show on sound. Today we're going to focus at quite a few of the practical applications that we look at when we work with sound. Sound forms part of the investigation into waves and wave properties. Now, although this is a very practical section in grade 11, when we get to grade 12, a huge section called the Doppler effect is based on our knowledge of sound. Let's get straight in and see what sound is all about. During this section, we are going to focus on sound and the ear. So a lot of the emphasis would be on the audible section on sound that we have. We're also going to look at the similarities that we have between light, sound, and water waves. Although these waves are different in terms of the types of waves that they do share common properties that we're going to investigate in this section. Moving on, we're also going to look at the specific properties for waves. Lastly, we're going to look a little bit at sonar and the practical applications of sonar in our daily lives. That would range from looking at sonar in terms of speed traps all the way through to the medical application thereof. Before we get into exactly how sound impacts on the ear and how those two work together, let's have a quick discussion on how exactly sound is generated. When sound is generated, air particles start vibrating. Sound is a form of a longitudinal wave. If you remember from the work that we did in grade 10, we have two types of waves. You've got a transversal wave where the disturbance is perpendicular to the direction in which the energy or the wave is propagated. So that perpendicular disturbance gives rise to a transversal wave. Let's look at a sketch of a transversal wave. For transversal waves, the disturbance occurs perpendicular to the direction in which my wave is moving. So these two meet at a 90-degree angle. This causes the wave to take on a sinusoidal graph or a graph similar to that of a wave moving through water. If we go and we compare that to a longitudinal wave, we see that the disturbance is parallel to the direction in which my wave is going to move. If this is the plane in which my wave moves, my disturbance will be parallel to that. This gives rise to waves that are formed through a series of compressions and rarefactions, as seen on the sketch over here. Just by comparison, if you go and you look at a transversal wave, you will have a crest or a trough. Now, the crest and the trough indicates the maximum or the minimum amount of energy that a specific wave has. If you go and you look at your longitudinal wave, you will see that the compression over here is the area where the maximum energy is experienced and the particles are pressed together. Over here where we encounter the rarefaction, that is where the particles are spaced out, and that is also where these particles will have the smallest amount of energy. So we will see here that for a longitudinal wave, we see that particles are pushed together, and when they move back to their original position, it leaves open a gap, and that is where our rarefaction occurs. So when you are speaking and sound is generated from your mouth, the air is being pushed out from your diaphragm, through your lungs, through your throat, and it goes through your voice box where the vocal cords start vibrating. This vibration creates a specific sound. We then manipulate this sound when we use our mouth in terms of our lips, our tongue, and our teeth. This causes the specific sounds to take on different intonations, and that is how we then speak and pronounce specific words. As the sound leaves our mouth, those air particles that come from our lip collide with particles in front of them, and these compressions move on until such a point where they lose all of their energy and the sound is no longer heard. If you do want to test this to see how it works, just put your hand in front of your mouth and repeat the consonant P. If you repeat that a couple of times, you will notice the movement of the air particles as it collide with your hand. Let's move on and look at sound and the ear. When these sound waves travel through the air and causes vibrations, these vibrations will reach the ear. Now please also note that not all vibrations are audible. When I use the word audible, I mean that not all vibrations can be heard. Audible, refers to hearing. So if we go and we look at the vibrations that we as human beings can hear, we see that as human beings, we can hear sound waves between the frequency of 20 and 20,000 hertz. Any sounds above that will not be audible, so we can't hear that, and any sound with a frequency of less than 20 hertz, we will also not be able to hear. Certain animals, however, have very well developed hearing, and they can hear sounds higher or lower than the frequencies that we as human beings can hear. So when these waves move with these frequencies, we see that they create compressions. These compressions move along a specific line. From over here we have a tuning fork, which is a musical instrument that we use to create specific sounds. The sound moves through the air towards the ear. Now in the ear you've got the eardrum, and the eardrum is basically a thin membrane that starts vibrating the moment the airwaves come into contact with that. That vibration is then picked up with the stirrup and the anvil, which are two small parts in your ear that pick up the sound. These vibrations are then decoded, and your brain deciphers that, and you get the message from your brain telling you exactly what the sound is that you heard. Obviously, if it's just a noise, your ears will start aching and your brain will tell you, stop, this is not a nice sound, we need to move on and listen to something more pleasant. If we go and we look at the flow diagram that we have on the screen over here, we will track the path of the sound as it is generated all the way through to the point where it reaches the brain. So the sound would be generated by the tuning fork. This is generated through a compression of air waves that carry a specific frequency. These air waves will push and pull on the ear. Remember, this happens through the eardrum that then vibrates and sends the message through to the anvil and the stirrup. These vibrations have the same frequency as the source, and that is very important over here, that the frequency does not change from when it was created until it is audible or heard. So your frequency does not change. The next step over here is the fact that this frequency is then strengthened or highlighted by the auditory bones. Those would be the anvil and the stirrup I was talking about a little bit earlier on. These messages are then transmitted and decoded by the auditory nerve in the brain, and that then transmits and decodes the information, which tells us exactly what the message is or the sound is that we heard earlier on. As you can see, it is a very simple process. If there is a disturbance anywhere along the path, it is going to impact on the sound that is heard. Just remember, if the problem occurs between the tuning fork and my ear, it will only be external, and any changes could affect that. But the moment the problem occurs where the sound enters the ear and goes to the brain, that path, that is going to be known as deafness or any other hearing problems that might arise from there. It is very difficult to treat such problems, and people that suffer from this generally end up being deaf for the rest of their life. Let's go and look at the similarities between sound waves, light waves, and water waves. Now, as I explained to you when I started off, there are two different types of waves. We've got our transversal waves that will create a sinusoidal wave, which is similar to that of water waves, and then we've got the longitudinal waves, which are a characteristic of sound. Now, if we go and we look at the comparison over here, we will see that, first of all waves will transmit energy. So this is a property that is part of all the waves that we look at. So all types of waves have that. all waves can be reflected. Do you still remember from grade 10 that reflection occurs when a wave hits a solid barrier and that wave then bounces off and stays on the same side of the barrier as it was before it struck the barrier? Now, sound waves, light waves, as well as water waves share this property. We're also going to look at refraction that occurs. Refraction refers to the property whereby when a sound or a wave reaches a barrier, the wave passes through the barrier, but because of the difference in the density in the barrier, this wave will change the direction as well as the velocity with which it moves. So we're going to look at these two properties a little bit closer. Over here, we look at reflection. If you look at these waves, which are waves that are generated in a ripple tank, you notice that the waves go towards the barrier at a specific angle. Now, using the information that we have over here, you see that the wave that goes towards the barrier is known as my incident wave. The angle that is generated over here between my incident wave and my normal is known as my angle of incidence. Now, some of you might ask over here, what is the normal that I'm talking about? The normal refers to a line that is drawn at a 90-degree angle with the surface of my barrier. So in this case, if you look over here, this thick line would represent a barrier. My normal is drawn at a 90-degree angle to my barrier, and my angle of incidence is situated between the normal and my incident wave or my incident ray. You will also notice that the moment my wave exits, it moves in a different direction. Now, the angle that I have over here is known as my angle of reflection. And this angle of reflection is equal to the angle of incidence. You will notice that I put a hat on top of my eye over there. Now, that hat that I put on top of my eye and on top of my R is an indication that I'm working with angles. So that is my incident angle and my reflected angle. And for reflection, these two angles are equal in size. So if we go and we bring that information across to this graph or this diagram, you will see that my reflected wave over here is moving at an angle over there. And if I were to go and draw in my normal line on this side, you would see that my angle of incidence that I have over here is equal to my angle of reflection that I have on the other side. And this is a characteristic of reflection, that your angle of incidence is equal to your angle of reflection. If we move on a little bit further, we go and we look at refraction. Now, we are going to specifically look at refraction on water waves. If we go and we look here, we will see that there is a difference in the depth of the water over here. Now, that difference in the depth can be equated to the difference in a medium. Now, if I have deep water and shallow water, the waves that move through the water will move at different velocities. If we look at that occurrence over here, you will see that this distance between two crests in my water waves will decrease significantly when I go from deep water to shallow water. This happens because the wave speeds up and moves faster the moment it goes into the shallow water. If we go and we look over here, where the separation between shallow water and deep water is at an angle, we will notice that these waves change their direction slightly. If I go and compare over there and draw my line down there, you would see that these lines don't follow on a straight line anymore. So they are no longer parallel to each other. So if there is a difference in my medium, or in this case the depth of the water, and the wave strikes that barrier or that separation at an angle, it is going to cause refraction that is going to cause my wave to bend. This is a very important property that we're going to look at a little bit later when we talk about sound and how sound travels through air with different temperatures. Remember that as air has a different temperature, the particles will be closer together or further apart. If the particles are close together, the density of the air is higher. And if my air wave would have to go and pass through those particles, it would be more difficult and it would slow down, and the path in which it travels will change slightly. We'll look at that just now. Now, when we see that the waves pass into the shallow water over here, we see that the wavelength decrease, as I indicated over here. And we also see that they change their direction, which we see over here, compared to the path that it followed over there. The other important thing over here is that it will have a change in speed, and that is a significant observation that you need to make over there. Now, the temperature of air will affect the speed of sound, as I've mentioned. If we look over here at the following diagram, you will see that we tell you that sound normally travels in horizontal lines. So if I look at my truck over here, which is signaling its horn, these sound waves on a normal day would travel straight in a horizontal line from the truck. But if I have an exceptionally warm day, these waves would move upwards because of the difference in temperature. As I've mentioned, if it is a warmer day, the air particles would be further apart, and that would cause the air to bend up, and that means that if you were standing in front of the truck, that it would be difficult for you to hear the sound waves. So if we go and we draw our little stick man over here, and he is standing on the side of the road in front of the truck, on a warm day, if the horn is signaled, he will not necessarily hear the horn quite as well as he would on a normal cool day. Now, the opposite is true for a cold day. If it is a very cold day, these air particles would be closer together, and because they are closer together, the waves would move slower. The moment the speed slows down for my wave particles, I see that they bend again. And if my man was standing in front of the truck now, he would definitely hear the sound wave of the truck horn that is being blown as the truck approaches him. Another application, and this is one that my science teacher told me when I was in high school, is in a cold winter's morning, when you have a rooster outside crowing, you're going to wake up immediately because you're going to hear the sound. And how inconvenient is that? Because the rooster obviously doesn't know that in winter time we want to sleep a little bit later. But during summer, when it's warm in the mornings and you want to get up early, you won't hear the rooster crow that well because the sound would be traveling up from where he is making his noise in the morning. Next, we're going to look at sonar. Sonar is a practical application whereby we look at how sound affects our daily life. We're going to look at it in 3 scenarios. First, we're going to look at the medical application. We're also going to look at how it helps us in industry. And then just for the fun of it, we'll quickly talk about how sonar and radar affects speed prosecution in South Africa. Now, those of you that have mothers, sisters, or other family members who have had babies in the last couple of months will know that when a baby is still in the womb, they use sonar to detect the movement and the growth of the child. What they do is they transmit ultrasound waves that are then reflected from the baby. These reflected waves are picked up by a transmitter and a receiver. The transmitter sends out the waves and the receiver will pick up the waves. These waves are then decoded and images are formed of the baby in the mother's womb. These images are then used to look for the gender of the baby, any deformalities that the child might have, or any other problems that might be encountered during pregnancy. During the second application, you will see that over here we also look at the industry. When we talk about the industry, we are going to look at the fishing industry, which by far uses sonar the most. Now, when boats travel along the ocean, they send out ultrasound not only to detect the depth of the ocean, but fishing trawlers also send out ultrasound to see where to go and catch the fish. They would send out the ultrasound, which is then reflected back from the different shoals of fish. The boat would receive these reflected sound waves, and they would go towards the schools of fish where fishing would then take place. All right, so lastly we're going to look at speed prosecution through radar. Now if you go and you look at the classical setup where we have a highway, and next to the highway you've got a traffic officer with the camera. Not only is this device fitted with a camera that will take a picture of your car, but this device also emits certain sound waves. These ultrasounds will then reflect off the back of your car, and as these waves are reflected back to the traffic officer where he is sitting, this device will pick up the frequency of the waves. If these waves are above a specific frequency, then they know that you are breaking the law, because frequency is directly proportional to the speed at which they are transmitted. So that is a very important relationship that we will be looking at a little bit later on as well when we do our calculations. This is just very simplified. As I said, we're only going to look at practical applications in terms of our calculations. Now, when we look at sonar and ultrasound, there are a couple of very important things that we need to remember. When we look at ultrasound over here, we'll see that for sonar as well as ultrasound, each of the scenarios that we looked at, whether it was for the medical purpose, where we looked at the baby inside the mother's womb, whether it was for the boat in the industry looking for the fish, or whether we looked over here at the traffic cop. In each one of these scenarios, we noticed that sound was sent out and it was reflected off a solid surface and then reflected back. So you had sound traveling in one direction and sound traveling in an opposite direction. Now, when we deal with scenarios like that in a calculation, it is important to remember that because the sound travels at a constant velocity, we need to look at the time that it travels towards the barrier and the time that it travels back. Now, the time towards my barrier and the time traveling back from my barrier would be exactly the same period of time. That is going to impact on our calculations. So let's look at a very quick example over here. We'll use the example of a boat that is sending out ultrasound to see how deep the ocean bed is or how far the ocean bed below the boat is situated. So if I have my little boat over here, and there's its flags, a nice little ship, and this boat is equipped with a radar or a sonar transmitter over there. This boat is going to send out ultrasound waves into the water. These waves would move until the point where they reach the ocean bed. So this boat would be out there to see how deep the ocean is. Now, if I tell you that the velocity of sound in water is 1,500 meters per second, we would know that because the water is more dense than air, the sound will travel faster. So it is going to travel downwards towards the bottom of the ocean with a velocity of 1,500 meters per second. The moment it reaches the bottom of the ocean, these waves are reflected back and they would go back towards the boat. Now, the boat would also be equipped over here with a receiver. Now, the purpose of the receiver is to pick up these reflected waves. It measures the time from when the sound is sent out from the boat until the time when the sound comes back to the boat. So if our receiver measures the time over here to be 8 seconds, and they ask us how deep is the ocean, so what is the distance between the boat and the ocean bed, we would approach the problem as follows. You have one of two options. Now, we can either go at looking to half the time that it takes for the sound to travel, because remember, the sound travels downward and it travels the same distance back up. And if the total time is 8 seconds, that means that it takes 4 seconds to travel down and another 4 seconds to come back up. So that would be our first option, is to go in half the time. Alternatively, if we use the total time, then we would see that we have the distance down and the distance up. So that would give us the total distance, but we're only interested in either the distance from the boat down to the bottom of the ocean or the distance that the sound traveled from the bottom of the ocean up to the boat. So we have two possible solutions over there, although they're going to give us the same answer. We're going to look at both ways of calculating this. Now your first option is going to half the time. Now when we do this, we go and we look at our information. We see that the velocity was 1,500 meters per second. I also told you that the total time, and that is then the time up and down, or in this case down and up, is given to you as 8 seconds. So therefore, the time that it takes for my sound to travel downwards, traveling down, so as the sound travels to the bottom of the ocean, is going to be 8 seconds, and I'm going to divide that by 2, and that would therefore give me 4 seconds. So when I go and I do my calculation, I'm going to use my velocity over there, and I'm going to use my time as the 4 seconds over here. So to find my total distance, it is going to be speed or velocity equal to the change in distance over the change in time. Go and substitute your values. The speed was given to you as 1,500 meters per second. The distance is unknown, and we are going to use the 4 seconds that we had calculated over here into our equation. So to find the change in distance, it is going to be 1,500 multiplied by 4. And that is therefore going to give us a total distance of 6,000 meters. Now that boat is quite far out into the deep ocean. Our second option would be to use the total time and to half the distance that the sound travels. If we do that, we're going to do the entire calculation using the total time, and we only have half our final answer. So let's do option 2 in a different color. Option 2, and what do we do for option 2? We are going to half the total distance traveled by my sound. So our information over here, we're going to use the velocity of sound in water as 1,500 meters per second. We're going to use our total time, which is 8 seconds. So if we use that information to go and find the distance, velocity is equal to the change in distance over the change in time. We use the velocity or the speed as 1,500. The change in distance is unknown, and the time over here would be 8 seconds. So the change in distance is going to be 1,500 multiplied by 8. And that is going to give us a total distance over here of 12,000 meters. But now, remember, the sound travels downward and up. And we are only interested in 1/2 of the distance that the sound travels. So to get our final answer over here, we would say, therefore, the distance traveled by the sound to the bottom of the ocean let's just correct that spelling, ocean, no, it was correct, is going to be your 12,000, and you're going to divide that by 2, which is going to give you your 6,000 meters. Now, both answers are the same. Both of them work out to give you a depth of 6,000 meters. Remember that you can use any one of the two approaches. If you remember to half the time, that is the approach that you use. If you've done the calculation and right at the end of the calculation you remember that you need to half the distance, then you're going to half the distance. The mark allocation is still going to be exactly the same for this question. Now, what happens when we have ultrasound and we go and we look at something like echolocation? Echolocation is the method of finding specific objects in a location that is used by animals. Two animals that are renowned for using this type of movement or location of stuff is dolphins and your bats. Now, they could ask you the same type of question as we had with a boat, and they can only change it and say that it is a bat that is emitting an ultrasound. The sound would then travel from the bat until it reaches the object, and it would then reflect back to the bat. And they could ask you to go and calculate the distance that the bat is from an object over there. The other animal, as I mentioned, is a dolphin. Dolphins also emit ultrasounds, and they use these ultrasounds that are then reflected back to them to move around the ocean and to find other groups of dolphins. Now remember, whether they give it to you as a boat or as an ultrasound machine to look at the baby inside a lady's womb, or whether they ask you to go and look for a speed trap or a question over here where they use animals, the same principle will still apply. Either half the time or half the total distance that the sound traveled during that specific time period. If you keep that in mind, these questions will not be a problem and you would be able to solve them very easily. Just remember that when we go and we look at sound waves, we are working with a longitudinal wave that looks at the compression of particles. When we work with light and water waves, we deal with transversal waves. All three of these examples follow the same rules for waves. In other words, they will behave exactly like all other wave particles. They will be reflected or they will be refracted once they reach a barrier. Also, what I would like to point out over here is the relationship that we have between speed and the frequency of a wave. Now, as my speed increases, I will notice that my frequency will also increase. And if my speed were to decrease, the frequency of my wave would decrease. This type of relationship is said to be directly proportional. The other relationship that is important for us over here is the relationship between frequency and wavelength. Now, the relationship over here is an inversely proportional relationship. That tells me that if my frequency for my wave is going to increase, that the wavelength will decrease. If you go and you look at a diagram over here, we can look at it in the following way. If my waves have a high frequency, they will be close together because many waves will pass a specific point in a certain period of time. Please note that the wavelength, which is the distance between two consecutive points over here, is a very small distance that separates those two crests. If I were to go and increase the frequency, or increase the wavelength, you will notice that as the wavelength gets bigger, I have fewer waves that pass the same point in the same period of time. And that is then our inverse proportional relationship that we have over here. Remember, a high frequency will result in a small wavelength, and a very small frequency would result in a big wavelength, which refers to the distance. So the wavelength over here would be measured along those 2 points. I hope that has put things into place for you. Let's look at some of the calculations that will help us to understand this section better. Question 1. Over here they give us a very nice diagram of a transversal wave. You will see that you've got a crest and you've got a trough over here. Now, the distance between the starting point, which is your nodal point over here, and the maximum displacement over there is called your amplitude. Now, the amplitude can be measured upwards, which is your maximum amplitude, or it can be measured downward, which is going to be your minimum amplitude. On this diagram, you can also see the wavelength. The wavelength is measured between two consecutive points in a wave. You'll see that just by looking at your graph first, that the particles, the amplitude over here is measured in millimeters, and the distance that the wave covers is measured in meters. So we see that our wave covers a total distance of 12 meters. They ask us, or they first tell us, that the speed of the wave from 0 or from O to A is 10 meters per second. So they're talking about the velocity or the speed that the wave has as it moves from that point all the way to A over there. And they tell us that that speed is 10 meters per second. They want us to go and find the wavelength of the wave if X and Y are in phase. So let's go and find X and Y on our graph. You'll see that X is the top of my wave over here, which is my crest, and Y is also situated at the top of my wave, which is another crest. Now, I've been talking about 2 points that are in phase. When a point is in phase on a wave, it means that the wave particles at that specific point is moving in the same direction and that they have the same velocity. Now, it is very important that they move in the same direction because it means that they also have the same energy at that specific point. Now, the easiest way to remember this is to go and look. If I'm talking about a complete wave, in a transversal wave, I should have one complete crest and one complete trough. Now, if you look over here, I had half a crest, and here I had a complete trough. So if you could find a complete crest and a complete trough within your diagram, then you know that that makes up one complete wavelength. So if we go and we look over here, the distance at Y is 10 meters. The distance at X is 2 meters. So my wavelength would be the difference between the two. So if they ask me over here the wavelength, I would go and look at the change in distance that I had over there between X and Y. We will see that it is 10 meters minus the 2 meters that I had at Y, and that is going to give me a total distance of 8 meters. So let's go back to our graph and see what we have there. We start measuring at 2 meters, 4 meters, 6 meters, 8 meters, 10 meters. So from 2 to 4 is 2 meters, plus another 2 gives me 4, plus another 2 gives me 6, plus the last 2 meters is going to give me my 8 meters. So that is then the total wavelength that we have between those two particles. Question 1.2 asks us, what is the frequency of the wave? So let's go and look at the possible calculations. Remember that they have given us over here, they have given us the speed with which the wave is moving through the water. We also just now went and calculated the wavelength. Remember, I said the wavelength would be a complete crest and a complete trough, which means that our wavelength over here is 8 meters. We are going to use the wave speed formula, which is velocity equal to frequency multiplied by the wavelength for the specific wave. The speed is given to us as 10 meters per second. Our frequency is unknown, and we have managed to find the wavelength over there on our graph as 8 meters. Now, to get our frequency on our own, our calculation would look as such. You divide by 8 on the right-hand side, and therefore divide by 8 on the left-hand side. So our frequency is equal to 10 divided by 8. Quickly put that into your calculator. 10 divided by 8, and that is going to give us a value of 5/4, or 1.25 hertz. So if we go and we write that down as our answer. Now this tells us, this 1.25 hertz, tells us that for one single wave to pass the point in 1 second, just over one complete wave would pass that specific point. And that is the time period that we have over there, or the frequency for that wave. Also, just remember, Hertz is named after the German scientist Heinrich Hertz, and Hertz stands for per second. Now later on when we go and we work with this formula again, you'll see that wavelength is measured in meters, frequency is measured in as per second, and that is exactly where we get the unit from that gives us our speed, which is meters per second. But we'll look at that again a little bit later. All right, if we move on to question 1.3, question 1.3 asks us, what is the period of the wave? Now, I've already scribbled on over here a little bit, and the period is basically the time that it takes for the wave to pass a specific point. But now over here, we are looking at one single wave that passes a point. Now, the relationship between period and frequency is that these two are inverted for each other. So if I go and I look, I'm going to have 1 over the value for my frequency that I just calculated, and that was 1,25 hertz. So if I go and I put this into my calculator, we'll just clear it from there. There's two possible options that you can do over here. You could say 1 divided by 1.25, and that is going to give you the value of 4 over 5, which is 0,8. Now that 0,8 is measured in seconds, so your answer over there is 0,8 seconds. And that is how long it's going to take for one single wave. The alternative option to calculate this is to use your inversion button over here. So that little button over there is going to invert whatever value you have. The value we had was 1.25. If we invert that value, press the equal to sign, you see that we get exactly the same answer. Now that inversion button is a nice shortcut if you have to do very quick work on your calculator. So keep that in mind. We also use it a lot when we work with calculating parallel resistance in electricity. So now that we've done the period, let's see what question 1.4 asks us. 1.4 wants to know how long does it take for the wave to move from O to A. O over here is the starting point of my wave, and A is the point where it terminates. They told us that the velocity or the speed of my wave is 10 meters per second. And we can see from our graph over here that the distance covered by the wave is a total of 12 meters. We're going to use the formula velocity is equal to the change in distance over the change in time, because we have a change in distance and we've got the velocity or the speed for this calculation. So our formula is speed is equal to the change in distance over the change in time. We use the 10 meters per second over here for our speed. The distance of 12 meters come from our graph, so it is going to be 12, and we need to find the change in time. If we take the time across, we see that it is going to be 12 divided by 10, and that gives us a total time of 1,2 seconds. Now the question was, how long does it take for the wave to move from O to A? And if we go and we look over here, it takes 0,8 seconds to move to there, and then half that time, which is 0,4, to travel that distance. So your 0,8 seconds and the 0,4 is going to add up to give you 1,2 seconds, which we did find in our calculation over there. So that is the total time that it takes for my wave to move across from the one point to the other. If we move along, we see that question 1.5 wants to know from us what is the amplitude of the wave. Now remember, I said in the beginning that the amplitude is going to be the maximum displacement from my starting point for my wave. If you go and you look at your graph over here, you see that this is the starting point from my wave. And the maximum displacement is going to be all the way to the top of my crest or all the way down to the dip of my trough. If I go and I look over here, I see that my crest is equal to 4. And the unit of measurement over there is millimeters. Now they did not specify over here whether it's an SI unit, but we're going to do it anyway. Our amplitude is equal to 4 millimeters, which when divided by 1,000 is going to give us 0,004 meters. Why do I want to work in the SI unit? As you would have noticed over here, our speed is given to us in the SI unit of meters per second. And in science, all distances are measured in the SI, or the standard unit measurement of meters. So it's always a good idea, unless otherwise asked, to give your answer in the appropriate SI unit for that specific measurement. We move on to question 2. In question 2, they tell us that sound travels through air, water, and glass. Now here we have 3 different phases. Air is the gas phase, water is the liquid phase, and glass is in the solid phase. If you quickly think back about the 3 different phases, you would remember that in the gas phase, the particles are far apart. If particles are far apart and they need to move in order to collide like they would when sound travels in air, these particles would have to travel great distances before the next collision would take place. With liquids, where the particles are closer together, the particles would not have to travel that far to transfer the energy of the moving particles. While in the solid phase, these particles are tightly packed together, one on top of the other. Any type of disturbance would mean that that energy is transferred very quickly through the solid material that we work with. So that is what we start off with for question 2. They ask us over here, through which medium would sound travel the fastest? Now, as I just said, we're going to look at the arrangement of the particles. The closer these particles are to each other, the faster the energy, in this case the sound, would travel through them. So the one that has got the closest or the tightest particle arrangement would be the glass, because the glass is in the solid phase. So where they ask me for the one where it travels the fastest, my answer would be glass. Now by comparison, water is a liquid, and over here air is a gas. Keep in mind that in the gas phase, the particles are far apart from each other. If they ask me for the medium where it would travel the slowest, it is going to be the one where the particles are the furthest apart, and that would be my gas. Just very quickly, the gas refers to the phase, and actually over here it is then air as your correct answer. 2.2 asks us to give a reason for our choice of answers in 2.1. And this is where you're going to refer back to the different phases that we have. So you're going to, for 2 marks, explain over here that in the solid phase, so in the solid phase of glass, the particles are packed closely together, allowing sound to travel very fast. Through that medium. In gases, these particles are further apart. Further apart. And the sound, let's just get that right, and the sound takes longer to travel through air. Now just remember, when I'm talking about these particles traveling, and I'm talking about sound that is traveling, sound is energy that is being transferred. So in the solid phase, the energy transfer takes place a lot faster when compared to this energy transfer taking place in air. Right, liquid is kind of in between, so it's going to be faster than air, but slower than solids. Question 2.3 gives us a bar chart that shows the frequencies of sound which different animals can make and hear. Now, as I mentioned a little bit earlier on, humans can only hear sounds between the frequency of 20 hertz and 20,000 hertz. Many other animals can hear sounds beyond those sounds that we as human beings can hear. So we've got bats, cats, dogs. All of these animals can hear sounds greater than the spectrum of sound that we can hear. So over here you'll see we have the human being, we've got a cat, a grasshopper, and a bat. Now by far the bat has got the best ability to transmit and hear certain frequencies of sound. They ask us over here which of the animals can make sounds which are beyond their own hearing in range. In that sense, which animals make sounds that they themselves cannot hear. So if we go and we look at our key over here, here are the frequencies for the sounds that animals can make, and these are the frequencies for sounds that animals can hear. Now if you go and look over here, human beings can only make sounds that they themselves can hear. The same goes for a cat. But if we look at the grasshopper can make sounds that go beyond the frequencies that they themselves can hear. They can only hear certain frequencies that are even less than the frequencies that we as human beings can hear. So the animal over here would be the grasshopper. So grasshoppers make sounds that not even they can hear. We move on to the next question. Still with a graph. They ask us what name is given to the sounds which a cat can hear but a human being cannot. If we go and we look over here at the sounds that a cat can hear the sounds that are above 20,000 hertz in frequency. Now that sound, because it is over, it is more, is referred to as ultrasound because it is greater. So the sound that I talk about over here is ultrasound. The next question. Now we move on to a bat. You'll remember from the graph that the bat can transmit, in other words, create sounds, and they can hear sounds that are far beyond the frequency range that we as human beings can hear. That is why bats can move around at night and we don't hear them making their screeching noises. Some of the noises are within the frequency range that we can hear, so you will be able to hear some of their screeches. Now, bats are fascinating animals. They are virtually blind, and they catch their food or they go and move around by transmitting sounds which are then reflected off obstacles. And when they hear these sounds reflected back to them, they can determine whereabouts these different objects and animals or insects are situated. They can then fly either towards it or away from it, and that is how bats use their ultrasound to see exactly where to go at night. Now they ask us over here to go and calculate the wavelength of the sound that a bat produces. Now the African bat produces a sound with a frequency of 212 kilohertz. The K in front over there is kilohertz, and that means that it is 1,000 times that specific frequency that is denoted over there. So we're going to have to do a conversion into SI units very quickly. Now over here for this question, one of the things that they forgot to give us over here is the speed at which sound moves. So let's see if we can get it from our earlier question over here. They only give us the frequency. All right, in such a case where the velocity of sound is not given, it would be safe for you to work with a speed of sound in air at roughly about 30 degrees Celsius as 340 meters per second. And that is exactly what we're going to do with this calculation. We're going to use the velocity of sound in air to be 340 meters per second. We have the frequency. Let's just quickly do a conversion over there. Now, frequency is given to us as 212 kilohertz. We want to work with the SI unit, which is just hertz, and the kilo over there stands for 1,000. So this would be 212 times 1,000 hertz. Alternatively, you could write it in the scientific notation, which is 212 times 10 to the power of 3 hertz. And there we've done our conversion. We are now going to use this together with the sound to go and calculate the wavelength. Remember the formula, which is the wave speed formula, where we use the velocity, we use the frequency of the wave, and we look at the wavelength. Now they've asked us for the wavelength over there. We substitute the velocity, which is 340 meters per second, the frequency, which is 212